Alright, in this video, we're going to take you way back to grade 9, maybe even at middle school, in order to prep you for the concept of some of the things we're learning in unit number 9. Today, we're going to be talking about rate of change, or otherwise we write ROC. ROC is measuring how much one thing has changed across the other, and you'll see some examples. There are two types of rate of change that you're going to learn about. The first one is average rate of change. That's what we're focusing on today. And then the other one is instantaneous rate of change. Average rate of change is the rate of change of a function over a given interval, so over a certain period. It might look like in square brackets, or it might say between two values. You're going to be given an interval. What we're doing is we're comparing the change in y with the change of x, and that's literally what we have written down here in this fraction. This symbol is actually the delta letter. It looks like a triangle, and it means change in. So we're saying, what is the change in y divided by the change in x? Okay, now this doesn't have to be super complicated. Let's look at our first example. I have a cat. Her name is Maple. I've had her for 4 months. When I first adopted her, she only weighed 7 pounds, but now she weighs 12. What is her average rate of change, and what does it mean in this context? So we need to figure out what are two variables here. We've got an independent and a dependent variable. The independent thing that's not sort of changing the other one is time. But her weight is dependent on time. That's the one that's increasing. In terms of time, we're starting at 0 months, right? And now I've had her for 4 months. And she started at 7 pounds. Now she's at 12 pounds. So our average rate of change, if we want to make it real fancy, our AROC is going to be 12 minus 7 divided by 4 minus 0. Okay, this should look very similar to your slope formula from grade 9. Okay, she has gone up 5 over 4, or about 1.25. And what does it mean in this sense? Well, 1.25 is how, on average, how many pounds that she gained per month. So on average, she gained 1.25 pounds per month. Another example. I drive a total of 35 kilometers to get to school, Bramalea. I take side streets, I take the highway, and I take main streets, which all have different speeds. On average, though, it takes me 25 minutes to get to school. What is my average rate of change? So in this case, my independent variable is the time, and my dependent is the distance. Okay. In terms of time, we know that it takes me 25 minutes. Sorry, I've got these backwards here. Yeah, the distance traveled doesn't change. What depends is the amount of time. So in this case, it's going to be 35 kilometers over 25 minutes. 35 over 25 is about 1.4, and so my average speed in this case is 1.4 kilometers per minute. That's what I'm looking for. Okay, there's lots of different rate of change questions you might be looking at. Hopefully you can think of one in your own head in terms of, something is changed per whatever. So for example, like your length of hair across time, right? The more time has passed, the longer your hair is going to be. Maybe it's amount of sleep across your age. So you think like children sleep a lot, and then teenagers sleep less than like babies do, but they still sleep a lot, and then like adults sleep less, and then like grandparents like sleep like very little. Maybe you want to be looking at like the growth of something. So like maybe your growth of your bank account over time. Lots of different things that you could be looking at the rate of change for. Okay. Another one here. So John rides his bicycle at a constant cruising speed along a flat road. He then decelerates as he climbs the hill. At the top, he accelerates on a flat road back to his constant cruising speed. Finally, he comes to another hill and glides to a stop as he starts to climb. Sketch a graph of John's speed versus time. So the speed here will be our y-axis. The amount of time that has elapsed is going to be our x-axis. And let's take a look what this might look like. So he's cruising along at a constant speed along a flat road. So he's moving constantly. His speed isn't changing. He then decelerates as he climbs a hill. So he's going down as he's climbing a hill. At the top, he accelerates on a flat road. So he's accelerating back to his constant cruising speed. Finally, he comes to another hill. So sorry, he's got a constant cruising speed. He comes to another hill and then glides to a stop as he starts to climb. So eventually, his speed is going to go all the way down to 0 because he glides to a stop there. Okay, this is what a graph of his different rates of change would look like. Okay, so we're at the start here. He decelerates and then he accelerates. We're back to the constant speed and then gliding to a stop. Okay, one last example to just sort of talk about the different ways that you could see rate of change. The average gas price per month in 2020 is given in the table below. Graph the points and connect them in a smooth line. What kind of function would best model this relationship? Okay, let's graph them. On our graph here, we'll assume that 1 is January, 12 is December along our x-axis. Okay, so on January, it was $114.70. February, it was $111.25. March, it was only 91. June, it was 98. It went up again. July was 104. August was 102. September was 101. Oh, hold on, I've missed one here. 114, 111, 91, 79. I missed the 79. Let's just move you guys all over by 1. Right, is that still good? May is at 91. June 98. Oh, we'll just redo them. It's okay. Okay. Here we go. April was at 79.83. It was all the way down here. May was at 91.08. June was at 98.80. July was 104.48. August was 102. September was 101. October was 99. November was 97. And December went back up to 104. Okay. So we were asked to graph the points and connect them in a smooth line, which I will do as smoothly as possible here. Beauty. Okay, what kind of function would best model this relationship? Think about the different types of functions we've seen. We've seen rational, we've seen exponential, we've seen polynomial, we've seen trigonometric. I'm going to say that this is probably going to be a polynomial function. At the end of the day, there's no periodic behavior. It doesn't look like there's any kind of asymptotes or anything sort of shooting off. And the polynomial will be able to grasp that we've got these hills and valleys present here. Okay, what is the average rate of change across all of 2020? So we'll say, well, what did we end at? We ended at 104.75. That was our price, but we started at 114. And that was over the span of technically 11 months, right? 12 minus 1. And 104.75 minus 114.70 divided by 11 is negative 0.90 approximately. And so on average, the price decreased by 0.90 per month. But we know that a lot more happened than that, so that's not really capturing it. But what this actually looks like, if we were to draw this on a graph, and I'll do it in red, okay, is if you were to connect a line from the start line, or the starting point, to the finish line. If that was a straight line, it would look something like this. We can see here that there is a slight decrease. Over time, and so it makes sense. So that's what that were to look like if you were to actually draw your average rate of change there. The next question, what is the average rate from March 2020 to September 2020? Okay, let's do this one in purple. March 2020 to September 2020. So September 2020 was 101.93. And then March was 91.13 divided by. September is the 9th month. March is the 3rd month. So we're going to have 101.93 take away 91.13, 10.8 divided by 6. Which is actually an increase of about 1.8 per month. So on average, the price increased by $1.80 per month between March and September. What does that look like? If we were to actually draw a line, again, start at March, end at September. September's right here, there we go. We can actually see that there is a slight increase here. And the answers that we got for question B and question C are actually the slopes of these lines, right? The red line matches with a slope of negative 0.9. On average, it's decreasing by that every month. The purple line here, we've got a slight increase starting from March all the way to September. Okay, what these lines are called are secant lines. A secant line is a line that connects 2 points on a curve. So just like what we did here where we connected 2 points on this curve. And it is the slope of the secant line that is the average rate of change across that interval. Okay, that is sort of the idea here, that we're dealing with secant lines and their slope tells us the average rate of change. Okay, so for example, we've got these functions here. Okay, 4 of them have been graphed. We're being asked to rank the following 4 functions according to the slopes of the secant lines on the interval between 1 and 5 using both the graph and algebraically. Okay. Note that we can't actually see 5. 5 is totally off the charts, so we're just going to have to look based on steepness. Just based on the graph, it looks to me that the green graph is number 1 in terms of steepness. It's the most vertical of all of them. And then maybe the black one. The red one is sort of hard to tell because it's upside down. I'm going to put that 3rd. And then the last one, the least steep, is the purple one. That's coming on down there. But we can actually calculate our rate of change for all of these across the 2 points. So let's do the green graph first. Our A rock, we're going to just use our function here, and we're going to substitute in 5 as our end value, 1 as our starting value. So it'll be 2 times 5 squared minus 2 times 1 squared, all divided by 5 minus 1. 5 squared is 25 times 2 is 50. 1 squared is 1 times 2 is 2, all divided by 4. 50 minus 2 is 48, divided by 4 is 12. Okay, next, let's do the purple graph. Same idea. A rock. We'll use our function. We have 1 over 2 times 5 squared minus 1 over 2 times 1 squared, all divided by, and I can just put a numerator or denominator 4. I know it's going to be 4 again. Okay, a half of 25 is 12 and a half. A half of 1 is 0.5, so I have 12.5 minus 5, that's just going to be 12, all divided by 4 is 3. Okay, huge difference in the A rock there between the green and the purple. Let's do black now. Okay, once again, A rock. And our black function is just an x squared. So I have 5 squared, take away 1 squared, divided by 4. That's 25 minus 1 over 4. 24 over 4 is just 6. And then the last one I have is my red graph. Our red graph is negative x squared. So our A rock will be negative 5 squared minus negative 1 squared divided by 4. So that'll be negative 25 plus negative 1. So that'll be a plus 1. Or sorry, take away negative 1, so that'll be plus 1, all divided by 4. That's negative 24 divided by 4, or negative 6. And so we can rank these in terms of steepness now. I think we can see that number 12, or the A rock of 12, is going to be the steepest. That's the highest one. So this will be number 1. Our green, just like we saw, green was the steepest graph. It was the most vertical. Turns out black and red are actually tied for second place. One is just shaped like a U and one is shaped like an N. And then our last one in last place, our least steep here, as we suspected, was the purple graph, and it only had an A rock of 3. Okay, another different question here. Given the graph below, determine the equation of the secant line between A and B. So Again, a secant line, if we were to draw it, is a straight line that connects those 2 points. So I'm going to connect A and B with a straight line. And I need to determine the equation of the straight line. This is the part that's going way back to your grade 9 days, okay? The very first thing we need to find is our slope. And for that, we need our 2 points. Point A seems to be located at 2, -1, and point B seems to be located at 6, 7. So I'm going to use my slope formula. Y2 minus Y1 equals or over X2 minus X1. So I'll have 7 take away -1 divided by 6 take away 2. 7 take away -1 is 8. 6 divided by 2 is 4. 8 over 4 is 2. So our slope here is 2. And now I need to figure out what my y-intercept is going to be. I plug in my m value. And then I'm also going to plug in the value of one of my coordinates. I'm going to pick the coordinate 2, -1. And I'm just going to rearrange here, and I'll get -5 is equal to b. So we can put both of these values together, and we can say the equation of our secant line from A to B is y equals 2x minus 5. Awesome. And our very last example here, just to sort of get you comfortable working with secant lines, the gas prices in Ontario across 2020, which we saw previously in example 4, can be approximated using this equation. F of x is equal to 1 over 32 x to the 4, take away x cubed, plus 11x squared, minus 47x, plus 157, where x represents the month of the year. From the equation, calculate the average rate of change of gas prices for the entire year. Okay? Entire year, I'm going to be interpreting that as between December and January. So as in month number 1 to month number 12. Okay? So our AROC will be our delta y over our delta x. And so that's going to be our function at 12, take away our function at 1, divided by 12 minus 1. Oof, this is going to be a lot to put in here. Let's figure out our function at 12 first. So it'll be 1 over 32 times 12 to the 4 minus 12 cubed plus 11 times 12 squared minus 47 times 12 plus 157. Woohoo, lots of math to do here. Okay, 12 to the power of 4 is 20,736. Divided by 32 is 648. 12 cubed is 1,728. 12 squared is 144 times 11 is 1,584. Oh, I wrote an X here instead of 12, okay. Minus, this will be 48, and then plus 157. Bring these all together. 648, take away 1,728, plus 1,584, minus 48, plus 157, is 613. One moment. It looks like I miswrote this. It's not 4 times 12, it's 47 times 12. That's going to affect this answer here. 47 times 12 is 564. Let me redo that calculation again. I'm going to get 97. There we go. That's better. Okay, let's try our function at 1 now. Okay, So I'll have 1 over 32 times 1 to the power of 4 minus 1 cubed plus 11 times 1 squared minus 47 times 1 plus 157. I'm going to jump to a decimal here. 1 to the power of 4 is just 1. Divided by 32 is 0.03125 minus 1 plus 11 minus 47 plus 157, and I'm just going to round this to 2 decimal places. It's going to be 120.03. So now we can actually go back to our AROC and we can calculate it now that we've done some of those. So our function at 12 is 97. Our function at 1 was 120.03, all divided by 11. 97 take away 120.03. Take away 120.03 is negative 2303. Divided by 11 is about negative 2.09. So on average, the price went down by $2.09 per month. Okay, and we can just look back to our example 4. Is that anywhere near what we got in example number 4? Okay, not exactly. And of course, our function, our polynomial function, is just an approximation. It's not like the actual thing. This is a better reflection of what our rate of change was. As you can see, we only went down by $10 across the 11 months. Whereas with our approximation here, with our formula, this was much higher. It was $23. So they're not, neither the function here that's been modeling it is not perfect. It is just an approximation. But we get the idea that we can do this from an equation and also from a table of values and a graph. Okay, and that's basically it. So the goal of this video was to warm you up to the idea of rates of change, what are secant lines, that sort of thing, and hopefully you'll feel comfortable seeing them in lots of different formats now.